Okay, so let's jump in. We'll work on this together. This will be interactive. And if you guys don't mind, I just texted Joe 8 minutes ago and he said he's not sure yet if he can come in, so he might just pop in. So we'll keep an eye on that.
Sounds good.
Okay, so today we're going to talk about the origin of lunar cold spots in ejecta rays. So let's define what they are first of all. This is, if you're not familiar, they are a very interesting phenomenon. Class of small, less than 2.5 kilometer diameter craters. They occur only on these smaller type craters, and they're visible in Diviner and LROC data. You know, and I think we add the LROC high resolution data, but they're really, I think, discovered with Diviner. So let's give credit where credit's due there. Cold spots, why they call that? The nighttime surface temperature is as much as 10 degrees Kelvin colder than surrounding, and then fades during the day. So this is all about thermal inertia. So why are these colder? Likely caused by lower density fluffing of the upper, just 10 centimeters or so of regolith. They're morphologically similar to all other small fresh lunar craters. So to the eye, to the visible light, they're not apparent. And these cold spot anomalies are not found in the interior, you know, inside on the floor of the crater, the wall of the crater. So that's the type of crater. So let's look at the similarities. So cold spot crater rays are similar to the visible rays, kind of wispy, ray-like morphology. They're radial to the crater. I mean, that makes sense. Spoke-like patterns. We see some examples here in the pictures. Some patterns are asymmetric as you go radially around the crater, you know, similar to regular ejecta. So I guess that's telling us that cold spots are following maybe the impact process in general. How are they different? How are the cold spot rays different from visible rays? Well, they're hugely longer, up to 100 crater radii. We see in this figure quite a distance. So I have another figure too that shows a visible light crater ray and a cold spot ray. So, and then this plot here just is comparing the crater diameter to the length of the ray, and we're seeing generally the bulk trend is that cold spot rays are longer. So what are the origin of these cold spot rays? Characteristics. Okay, so cold spot ray craters typically also include visible rays. So yeah, I don't know that we found craters that only have cold spot rays. You know, it's generally a mix because these are fresh craters. Cold spot rays don't persist for a long time. And cold spot rays form before high albedo visible rays. This is the figure I was thinking of here in the colored version, where we see a crater ray, a visible crater ray, and then the cold spot ray extending well beyond that. So with that kind of extension, what does that imply? It implies some pretty good energy behind the generation of these. Okay, so currently we document 3 proposed models for formation. Okay, first one is impact ejecta. So we have these visible rays that's clearly impact ejecta, and we might have kind of a different form of a regular impact ejecta ray that reduces the bulk density of the regolith In other words, again, it's got to do some kind of fluffing of the regolith to reduce the density in order to have this cold characteristic. So maybe small secondaries, very small secondaries, are mixing with the regolith, fluffing it up, and only affect the upper few tens of centimeters of regolith. And then what's different about these rays compared to the other, they're not digging down and exposing fresh material, which would be lighter in color in a typical ray. And then I think Joe kind of puts a counter argument here in parentheses, italics. So the counter argument to impact ejecta is, but no model is proposed for how ejecta rays could be composed of mainly high velocity small particles. Next, let's look at impact gas flow as an origin. So regolith fluffing up due to high velocity flow of gas laterally across the surface has been proposed, and this would be caused by impact vaporization of volatile rich projectile material. But generally not enough gas exists in impacts to produce these long rays. And then maybe, I think we talked about this yesterday, somebody mentioned seismic shaking associated with the impact of the primary crater. But generally it's thought that seismic shaking would compact or increase the bulk density, lowering the thermal inertia. So to a first order, most reasonably, though incomplete model for origin, just going back to first principles, really is, let's look at the impact process itself. The physical characteristics of cold spots and the ray suggest they're just another aspect of the crater impact process or facies of the impact ejecta. And this would be produced early in the formation because cold spot rays underlie or superposed by regular rays. So going back to Meloche and others, the traditional impact crater ejection sequence, going from earliest in the process to latest, we explore each of these three items here. First, the vapor plume, then jetting, and then spallation. And again, we're looking for a possible origin. So vapor plumes, it's basically a rapidly expanding cloud of vapor and impact produced mainly by impact vaporization of the projectile. So it occurs very early in crater formation before the crater opens up. Very high velocity ejection. Material is ejected at nearly the velocity of the impacting projectile, i.e. higher than the escape velocity. And I think as we go through these three parts of the ejecta process, it's kind of good to key in on the velocity of what's going on in each process. So very high, but this is still, it could be higher. So these highly shocked materials condense to form very small particles, sub-millimeter, but very little ejecta material is ejected, likely too little to generate detectable deposits. So currently there's no mechanism identified for an expanding plume to form rays. So consequently, in this talk, we do not consider this process, the vapor plume process, as a viable possibility for the origin of cold spot rays. Next, let's look at the second in the sequence, jetting. Jets are produced by the oblique convergence of impacting projectile curving sides and the initially flat target surface. Of course, when we're talking about a projectile and we look at a textbook or Meloche or whatever, we see a perfectly spherical target hitting a perfectly flat surface. So Let's keep that in mind. That might not be the case. So here's a good word, squirt. Jets squirt from the interface between target and projectile during the projectile's penetration. Jetting occurs early, usually completed before the projectile fully compresses and basically before it's halfway into the target. So that's a very small slice of time. And here is where we get to the model. Irregularities in the topography causes contact angle between the projectile and the target to vary azimuthally, resulting in jets that generate instabilities that produce discrete rays. So yeah, sure, that's how you get a variation. And that works with visible rays too. So jets can be very high velocity, several times the projectile's velocity, depending on the impact angle. So I think that's a key component. Jetting is generally comes out at a higher velocity than the vapor plume. So jets are composed of shock mixture of vapor melted and small solid particles of both the target and the projectile. And the mass is generally small, somewhat, and depends on the angle. The jetted vapor and melt condenses to form very small particles, again, submillimeter. So here's a diagram from Meloche 89 showing jets kind of on the left-hand side of each of these three diagrams. Each one of these are modeled at the same velocity, 6.5 kilometers a second. The only variation is the impact angle. It's 10 degrees, 25, and 45. And at a low angle projectile, we're getting might get a little jetting, but it's going right into the surface. It's not projected at a distance. But as the impact angle increases toward the nadir, then we get more jetting that can go off at a distance. We're running off the slide here. So the third mechanism is spallation. Small plates are produced by interference near the free surface between the impact stress wave and rarefication wave. So there's some reflection back and forth. And so these waves can add particle velocities to overcome the tensile strength of the target and expel surface material, forming spall plates. Got a diagram on this I'll show you in a second. So small plate ejection occurs after jetting and the vapor cloud formation, but it's still before the classic excavation part of the impact. Spalls can be high velocity, as much as twice the velocity of a stress wave. Spall plates are larger than the Grady-Kip fragments for a given ejection velocity. They have so much elastic energy that they fragment into smaller particles soon after ejection. So Meloche does suggest that although the volume of spalls is only about 1 to 3% of the total material, they're probably responsible for secondary crater fields, including visible rays. Yeah, of course, 1989 was before cold spots were discovered. So here's a diagram showing the spall generation. It's basically a lifting of the material, pre-existing material around the crater by the expanding pressure wave. So let's just get to our conclusions based on the evidence we've looked at. So considering the characteristics of cold spot rays, jetting is by far the most likely origin of these rays. That's that second process that we discussed. They're produced before other ejecta facies, such as continuous, discontinuous ejecta, and visible rays. So it meets that criteria. They are the highest velocity form of the three phenomena we discussed. So that results in a long range for these for a given size crater. dominated by abundant small ejectable particles. So you need some kind of material to lift the regolith and impart space and fluff. But they might be small enough that they don't produce visible secondary rays or thick deposits. Impact of these small particles would likely affect only the upper regolith surface. Total ejected mass is too small to be enough when mixed with the regolith to be identifiable as fresh material. And we'll just leave it on that slide there.
All right.
Something popped up.
Yeah, we do not need Microsoft to access my camera.
All right.
So keep in mind that we got this presentation yesterday, and giving someone else's presentation is very difficult. We've done that once at PCC before. Now we have a second time, although in this case there was at least some advance warning.
So let's discuss. I mean, it's an interesting topic. I didn't want it to just be put off for the next year or something.
Yeah, this is really cool. So you said that jetting doesn't quite happen as much in really oblique impacts. Do we see cold spot of rays around more oblique impacts? Like, is that kind of a common thing? Or like,
You're saying that the cold spot would be closer to the crater in the
yeah,
impact
that's
site.
kind of my idea that I'm getting at, is like, it would be interesting to see, like, if you could make kind of a relationship between obliquity and the length of these like cold spot rays.
Yeah.
Cool.
Okay. Well, let's deconstruct this just a little bit. Keep in mind, Joe didn't see the figure that I added to his talk last night.
Yeah.
So we didn't really discuss the angle business.
Yeah.
But so, what I think what's going to happen is cold spots are maybe generated closer into the crater, but you're overwhelmed by the ejecta. Then you're bringing the cold spot. So these smaller craters, we're getting some separation because of the velocity. So
Like the cold spots like start farther away from the crater, or
yeah. So let's rephrase. So with your high or low angle impact, you probably have all the processes going on. You've got a cold spot generated, then you're just burying it with ejecta. So we're just not going to see it.
so you don't really see cold spots around oblique?
Not that I know of.
Okay.
I think another way to look at it is are all the
Azimuthally, like irregular.
azimuthally. I like that
Like,
word, by the
that would
way.
be, yeah. Maybe that would be like, I don't know, I was thinking those would be the oblique impacts where you have those like biased sides, like of cold
I
spot.
think the first way to test this would be do we have any oblique identified cold spot craters?
Yeah.
So I was gonna comment on that too, of just that there's a Herrick and Forsberg Taylor paper where they were just looking at trying to find like the butterfly pattern and the zone of avoidance. And I've always thought it was very clever that they just did that by looking at the histogram of how often these craters formed, knowing roughly what the distribution of impact angles would be. And I wonder if you could do a similar thing with this. If you do think it's jetting, not necessarily looking at the length of the rays, but just trying to do a histogram of all of the craters of roughly the size and age, do the cold spot craters show up in roughly the amount you would expect for only the most oblique impacts?
I should also note there's a new list of cold spots probably coming up because Diviner has been improved. And so thermal temperature anomaly has been improved. And so they're working on a new, like adding on new cold spots, which were too small initially to see, or were also maybe faded to the background. And so there's a whole new group of craters that are going to be added to this list at some point.
Okay.
So, and then also I think the reason we're seeing this, like the cold spot forming distally from the rim, it's kind of what you said, this like it's just hot near the rim. Like you got a lot of rocks. So they're out competing the regolith fluffiness that's happening further away from the crater.
Oh yeah, all your boulders are kind of disturbing these cold spots.
Exactly. So like it's possible the regolith is fluffed in that region, but the rocks are just dominating that signal.
Yeah. They quickly take over.
Yeah.
Yeah, thanks. So that's following a normal progression. new instrument, new data. First, we make a discovery, and then we've got a few, and then we quickly want to add to the data set. And
Yeah,
then we can start to see trends and draw conclusions.
I'm gonna
Anything online?
There has not been any questions
Okay.
specifically online,
Yeah.
so go for it.
keep harping on target material again. It's like the last talk, but I think it might be interesting to look at like target material and target porosity and where these cold spots are showing up crater wise. So like maybe the target properties and impact mechanics could affect whether the cold spots show up or not.
Oh, I think that's excellent. Marley, do we have any cold spots in the Highlands?
we do loads.
Oh, really?
Yeah,
Okay.
We basically see.
So that's the first order material difference
Yeah.
right there. I didn't know that. So,
We see them around basically every fresh impact, at least all the ones that have formed during
okay.
LRO.
Regardless of
Yeah.
hemisphere.
Yeah.
yeah,
Basically
regardless.
uniform.
It's leading trailing asymmetry. But not for the big ones. All the big ones are not following this asymmetry.
So it's probably not a target material.
Yeah.
process,
Well,
it's probably
there
impact.
is suggestions that the rays are seismic shaking, which would mean that you need
That
some
was-
variability in the subsurface.
I think Nick Schmer did a talk
Yes.
at LPSC about the cold spots and seismic.
And seismic,
radiation.
right.
Yeah.
Yeah, I think it's all of those objections about seismic shaking were correct, but there's been some new modeling that shows you can fluff up when the seismic wave basically reaches the interface of the surface and the vacuum of space. You can impart a vertical force to the regular particles. But then another objection to seismic shaking is that the seismic wave would be basically radially symmetric. So
I was just
that would-
gonna ask, so these are circular or radial too, but it doesn't seem like the images that I've seen.
No, yeah,
They're
it's very,
more
very asymmetric in
ray-like,
these rays,
so-
but talk at LPSC showed that if the seismic wave is propagating through a heterogeneous medium, basically if you have a bunch of boulders and fragments in the subsurface, then the seismic wave will propagate and get concentrated along the contacts between the boulders. And so you actually get this highly asymmetric and spoke-like pattern of the seismic wave. So now it's sort of coming back as a possible hypothesis.
Interesting.
So we do actually have two questions online also, so I'm gonna let Alex ask questions first. Can you just gonna turn on your mic?
Thank you. I didn't want to type it because it's complicated. First of all, I was really looking forward to this talk, and it's really cool that this is getting dissected. Do you have any thoughts on the role that the radiation could potentially be playing in this, and what the effects of this would be if it was radiation on the signal that you get from a diviner? And just about some context, why am I asking this question? And that is, there are some laboratory experiments from John Tandy, etc., people using light gas guns that show that during the impact process, early on sometimes and under some conditions, there will be some sort of like a peak in radiation, maybe that is directional, kind of related to jetting. The other reason why I'm thinking about this is because there will be some probably heterogeneities in the vapor plume, and maybe there's some aspects that make the opacity of the that allows to escape the radiation also not homogeneous. So maybe you could get some sort of a pattern like this as well. So anyway, do you have any thoughts on radiation? Have you considered this? What it would do to the target?
No, that's intriguing, and we have not considered that. I mean, we did go back to kind of the core impact process, and I don't think Milosh gets into radiation, so we'd have to consult other sources. And this is open for the room as well, if anybody has any knowledge in that area. Okay, we'll have to dig more into that later. Thanks for the question.
Looking forward to hearing what you're gonna find. For real.
Wasn't there a second one?
Yeah, so Olivia was the next one.
Hey, Tom.
Hey there, Leah.
Fun. So I can't believe it's over 20 years ago, but there's the paper from my Mars work on raid craters.
Okay,
And one of the things that really stood out about the rays is that they're colder than their surroundings. Additionally, these craters seem to contrast best in the thermal data where you were into a specific thermophysical unit that represented an intermediate dust cover. And by combining the thermal observations with high resolution observations, it seemed like the most logical explanation was that the finds in this intermediate, this intermediate dust covered surface, it's being remobilized by secondaries seems to be what produces these cold rays. So I'm kind of wondering if maybe something like this is also operating here. The other thing that struck me was that you're only seeing this around smaller craters. So whatever's going on here, it sounds like it's even like crater rays are ephemeral, but maybe these are even more ephemeral.
yeah,
Because
I'm
there are
pretty sure that's true.
a smaller and more recent phenomenon. And so I can see where these are, maybe larger ray craters also had a colder signature with their rays, but basically space weathering has messed that up over time.
Yeah, so we've got a bias by size just because large impacts are less frequent, tend to be older.
Yep.
We need a large impact.
Yeah.
Please order that.
Per Mark's talk yesterday, the thing with the numbers and the letters might hit the moon, what was it, 4 years? It didn't hit this year?
Yeah.
Yeah, could be on its way. But yeah, good thought, Livia. Thanks for that. I think that fits in. Yes, and so you're kind of saying that, yeah, back to the ejecta theory. I mean, you're going to get a variety of sizes with the ejecta material. So why not some fluffing with that? I think there's more work to do in this area.
Yeah. Anyway, have a look at that 2006 paper, see if, I don't know if there's anything worth noting from the Martian raid craters with respect to these. So
Yep, will do. Feel free to contribute to the chat as well.
sure thing.
Always
Great
welcome.
talk. Thanks.
Thank you.
Maybe one more question. Or else we have 1 minute until the lunch break.
We can always go to lunch early.
1 minute early. All right,
Oh,
let's,
I just-
yes.